So we'll be talking about as to how we can determine surface area and pore size of our samples. The samples could be powders, could be formed materials like pellets or uh, there's any form that you can think of. So long as they have something to offer for adsorption, they will be measured. And when I say something to offer for adsorption, I mean measurable adsorption. Okay. The word measurable important because we know every surface that we see around us or around us will absorb gases. Only thing is, in most of the cases, we can't measure it. The quantity of adsorption is so small that we can't measure it. So we have to create certain conditions, the conditions which will enhance adsorption so that adsorption becomes measurable. Okay. So we are talking about from such gas adsorption measurements, how do we find out surface area and pore sizes? Okay. Well, surface area, as you know, the most important reason why we want to measure surface area is surface area will affect reactions. It could be physical reactions, it could be chemical reactions. Vaporization, physical phenomena, but will be enhanced by the enhancement in the surface area, and any other chemical reactions, especially taking place in presence of a powder, will be dependent on the powder's particle surface area, that particles that go to make that powder. Very common, but not a very good example is that aluminium powder. If you take a piece of aluminium, it's harmless. But if you have the same aluminium in the powder form, a fine powder form, and just give it a bit of air, it will start burning. That's the rate of reaction increases because the particle size has come down or the surface area is increased. So it's basically, we want to measure surface area because it affects the reactions, both chemical as well as physical. And the gas adsorption experiment, the purpose of gas adsorption experiment could be one or all of them: to measure surface area, to find out pore structure, which means pore sizes and total pore volume. It also measures the total adsorption capacities, or what you call as total pore volume. So how much will a particular material adsorb can be found out from gas adsorption experiment. And some chemical properties related phenomena like chemisorptions and other things. This is in all what the purpose is. Whether you will be doing a high pressure or whether you will be doing a normal sub-ambient pressure experiments, one of these will be your purpose. Nothing great in what I'm showing you right now. Basically, the first thing that you see is which is n equals function of whatever. What basically it means is, instead of saying it in words, I have written it in mathematical form. Amount adsorbed will depend on the mass of the material, which means the total area of the material. At pressure, it will also be a function of temperature. It will be a function of the nature of the gas that you want to adsorb, and it is a function also of the nature of the solid on which you are trying to adsorb. In such functional equations, what is interesting is you can take any of these out by keeping that thing as constant, by keeping that parameter as constant. For example, I can say that on a on a given solid, that amount of adsorption will depend on mass, pressure, temperature, and the nature of the gas. I can also take out gas and say that on a given solid, the total adsorbed amount of a given gas will depend on mass, pressure, and temperature. Keep on doing that. At the end of it, you can find out that total amount of a particular gas on a particular solid at a fixed temperature is a function of pressure. Now, this fixed temperature, total amount, and fixed temperature, which means we are talking about the amount at a fixed temperature, means we are talking about an isotherm. Since it is a gas measurement, the total amount is usually expressed in volume, because that's a property which can be measured easily. So volume of an adsorbed gas as a function of pressure at fixed temperature is an equation for isotherm. And that's why when we measure with this instrument, we are measuring the adsorption isotherms. Pressure is normally normalized to its saturation pressure. I might tell you the reasons why it is required, but it's a good thing that you normalize the pressure with respect to its saturation pressure and express pressure as P by P0. When it is expressed as a ratio, then we call it relative pressure. Okay. Generalized experiment will look something like this. Your sample tube where you are keeping this sample is connected to a vacuum source, is connected to a couple of gases like nitrogen, also with helium. It is also connected to a pressure measuring device, which is transducer in this case. What you are seeing is that this sample tube is dipped into liquid nitrogen bath. Remember when I was mentioning that quantity adsorbed as a function of whatever, adsorption quantities increase when you lower the temperature and decrease when you raise the temperature in any given conditions. So in order to make a measurable adsorption measurement, we have to cool the sample so that the amount adsorbed increases and we are in a position to measure it. That's why, and the best way to cool it, and because the temperature needs to be constant throughout the experiment, we need to find an easy way to keep it to a particularly low temperature. The best way is, if you are using nitrogen gas as a gas which you want to adsorb, if you are using nitrogen gas, cool it to the liquid nitrogen temperature. A liquid nitrogen temperature, so long as liquid stays there, a constant temperature is provided. Of course, what goes without saying now, because you have already heard it yesterday, you have to prepare the sample. After the samples have been transferred to the instrument, sorry about it. You start by evacuating the sample, because when you were preparing it, before you transferred it to the sample tube, you had filled it with the gas. Okay. Now, once we start the experiment, we have to start from the vacuum. Okay. So you have to evacuate it. Once it is evacuated nicely, when it is under vacuum, then you start dosing your adsorptive gas. Adsorptive means the gas that you are for which you are trying to study the adsorption. So adsorptive gas in most of the cases is nitrogen. for very good reasons. Start measuring the equilibrium pressures, calculate the volume adsorbed. Remember, volume adsorbed is not a measurement here. Volume adsorbed is a calculation. And once you get the value of volume adsorbed versus the equilibrium pressure, repeat those cycles and get the entire isotherm. Just few things, because I have written here under point 4, calculate volume adsorbed. Remember, volume adsorbed is always a calculation. And these calculations, which are of course done by the computer, these calculations require what is known as free space. So the next slide, we have defined what the free space is. It's the volume of this tube minus volume of the sample is the free space. Remember, this is just the tube in which you keep your sample, but above the tube there will be walls which are closing it, and then there will be a transducer to measure the pressure. So the space between this and the wall above, and then the space up to the transducer, these are all this is all included in the free space. Okay. Now, what do we require to make an isotherm? You need a sample pressure measurement. You need a saturation pressure measurement, because we need to normalize the pressures. And then we will calculate volume adsorbed from these 3 points: sample pressure, free space, and manifold pressure and volume. Manifold is nothing but a small space above the sample tube, which collects the gas from the cylinders or whatever the source is before it starts dosing onto the sample. And this manifold pressure and volume have to be known precisely. Pressure, of course, can be measured. Volume is basically a pre-known quantity. You have to know the volume before you can do it. Okay, you can do the experiment. This volume is part of what we call calibrations. So if something happens, and if some is somebody trying to say something? Hello?
Yes, sir.
I heard some cross talking. I thought somebody was trying to say something. Anyway, doesn't matter. Now, important thing about what I was telling so far was that all these measurements have to be done at equilibrium conditions. Important comment on the side is that the adsorption experiments take quite long times. Basically, adsorption is a slow phenomena governed by diffusion of the gas into the spaces within the sample, within the particles, within the samples. And this diffusion, as you know, is a thermodynamic process. Low temperature doesn't help it. Actually, a low temperature of the experiment makes it hard to diffuse, and that's why adsorption process is a slow process, especially at very, very low pressures. It takes long times to complete the total experiment. I mean, how does this statement gel with the slide? Because all this free space and your liquid nitrogen has to last for this long durations. Free space needs to be maintained at the same value as it was when the experiment started. It has to be maintained throughout the experiment. Okay, these two things, that's why the long duration has been mentioned here. The typical data in the tabular form looks like this. You have relative pressure, absolute pressure also you mentioned, quantity adsorbed, and how much time it has taken. Okay, and saturation pressure measurement. Other things are some of the parameters that you have used, for example, weight of the samples and all those things. Typical results will look like this. Okay, so this is basically what comes out of the instruments, a typical isotherm. I'm not mentioning what this material is and other things, but this is how the typical isotherm will look like. In the tabular form, it will look like this, and in the basically as a graph, it will look like this. Just a couple of things I want to mention. There are low surface area materials and there are high surface area materials. Roughly, it gets transferred to, there are low adsorbing materials and there are high adsorbing materials. The situation, and by the way, one more thing which I missed out. How does the instrument calculate volume adsorbed? Basically, the amount of the gas sent in and the amount of the gas remaining above the sample, which means the amount of the gas which has not been adsorbed. So amount of the total gas sent in minus the amount which remains above the sample in unadsorbed form is your value of adsorbed volumes. Okay. Now, if you're having a low surface area material, which means it will adsorb very less, which in another word means that if you have sent 1,000 molecules to the sample, a low surface area material, especially at low pressures, the situation will be that 998 will remain above the sample and only 2 molecules will be adsorbed. Okay. Now, it's quite a common sense that getting a precision of your measurement in such a situation where you have to deduct one quantity which is almost equal to the quantity that you want to deduct it from, the precision of the calculations are likely to be not so precise. So we have to create a situation where the total amount of the gas and the amount remaining, there is quite a nice gap there. Okay, so that the calculations come out correct. It is for this reason we sometimes have to change from nitrogen to some other gas if our materials are very low adsorbing. For example, if you put your glass beads, I'm talking about the glass which are non-porous glasses. If you put those glass beads as your sample and want to run a nitrogen experiment in the normal instruments, nitrogen adsorption, I don't think you'll get any data there. There won't be any adsorption, measurable adsorption there. Because the situation will be like this. All the gas that you wanted to send it remain on above the sample with very few molecules adsorbed, and that calculation is not a very good calculation. So with the result, we need to change from nitrogen to some other gas. I'll talk about it later if there is a read. Most of you will not. I mean, this situation arises in a very, very few cases, but let me give you some quantitative also idea. If your samples have, let's say, about 0.1 meter square or less, you probably will find it difficult to measure using nitrogen gas. Let me put it this way. And there are quite a few samples like this. It's not that I'm talking about a utopian situation where you don't see those situations. You will see those situations many times, especially those people Those of you who are coming from pharmaceutical industry, that is quite a normal practice. Another important thing, this was low pressure versus high, low adsorption versus high adsorption uh, discrepancies. Another thing is your equilibration. Remember, the very first slide, second or third slide, I said all these measurements need to be at equilibrium conditions. The reason I said that was because all the modeling or all the equation that you want to use either to find out surface area, all those equations assume equilibrations. Okay, so your data has to be equilibrated. If your data is an equilibration means good equilibration. The data that I'm showing is also equilibrated, but not completely. And I might, a non-equilibrated data might give you, depending on the nature of the sample, might give you a difference of about 30 or 40% in all the values, whether it is pore sizes or pore volumes or surface areas. Okay. In this slide, can you see this graph with the red pen? Can all of you see this?
Yes, sir.
Okay. This is an unequilibrated data. Okay, deliberately acquired unequilibrated data. Next point, this point that you see from here to here, this point was equilibrated, which means if I were to equilibrate all the data, the isotherm should have looked like this, not this. It would be looking like this. I'm sorry. Yeah, this is a slightly larger picture. This is slightly larger picture. You can see it easily. The isotherm should have been like this. This difference itself is quite high when it comes to surface area measurement. You should expect a big error in this case. Even isotherms, isotherm will in unequilibrated isotherm you will find is quite narrow. A fully equilibrated isotherm should be slightly broader. Let me see if I can see some isotherm, I'll tell you. These are some examples. Sorry, I wanted to shift it. Looks like I can't do it. Yeah. These are some examples of the type of the isotherm that you might come across. It's a non-porous or a macroporous material where the increase in the adsorbed quantity goes almost linear right up to the end, and then it starts increasing for more than one reason. I'll come to that. Next one is a high surface area material like MCM41. Okay. Third example is a micropore sample. See, you see some microporous. One is used to seeing the Langmuir type isotherm like this. Okay, a steep vertical right in the beginning and then almost horizontal after that. Only thing is you see steep vertical because the x-axis is normally plotted in the normal thing. If you plot the x-axis in the logarithmic scale, then you will find out that steep vertical is actually looking like this. Okay. This also is the reason why certain initial thoughts which were pertaining to adsorption in the micropores. People thought that micropores adsorption means as soon as you reach a particular pressure, a particular size of micropore will fill immediately. Okay, then increase the pressure and a particular micropore will fill instantaneously. There is no instantaneous filling here. Okay? And the reason is, had it been instantaneous filling, then you would see steep rise like this at every place. It's a gradual filling of your micropores, and it is after studying this particular area of your isotherm, you will find out the micropore size distribution. This is an example of single wall carbon nanotube, so it's only microporous samples. Yeah, you have seen this equation so many times, must have got bored with it. But yes, I'm not talking about the equations as much. What I will be talking about, the next. Okay. This is the BET curve on the right hand side. This is the BET curve. From the whole isotherm, we have taken these points. I mean, it's not the complete isotherm. Few points of the isotherm have been taken for calculation of the BET area, or surface area. The points are 0.05, 0.07 up to 0.29. Okay. They give you a nice straight line in this case, and well, you get surface area. It's a standard reference material, silica alumina, 215. Something interesting will come. There are C constants which appear in this equation. It's a very important. It's a very important constant. One must really take cognizance of, or must really take care of it. When you get surface area values, the calculations will also tell you what is the C value. Okay. It will also tell you what the y-intercept would be. This equation has to cut y-axis on the positive side. So this small thing is a y-intercept. This small thing is a y-intercept. This needs to be positive. C has to be positive. C is basically net heat of adsorption, an indication of net heat of adsorption. Okay. If you are having an adsorption, you can't afford to be having a negative C. Another thing is, when you have negative C, if you have negative C, the equation actually you won't have this kind of curve. Okay. Negative C, that's why is not so physically possible. If it is coming in your results, it's for a different reason. And we'll talk about those reasons, because I've seen many people not quite understanding it when they are seeing those results. Similarly, y-intercept cannot be negative. If y-intercept is negative, that means you are trying to measure some adsorption. You are trying to measure some adsorption which is negative. I mean, negative adsorption doesn't make a sense. And that's why intercept cannot be negative and C values cannot be negative. C values being negative also has an indirect meaning. You know, when I said net heat of adsorption, net heat of or energy of adsorption, there are two things that are happening. One is your molecules that are coming onto the surface, they have an affinity with the surface. So there's some forces there. Another thing is these molecules might interact with themselves. Okay. So when C value being negative means that force of attraction between your molecule, gas molecule, and the surface is less as compared with the force of attraction among the nitrogen molecules themselves. Okay. Which basically means this attraction among the molecules is is something which is related to the liquefaction of the gases, and it's not something which should happen while doing adsorption. But if you get C value very high, which means uh, there is very strong interaction with nitrogen gas with surface, and low value means weak interaction of nitrogen with surface. Negative value means interaction between nitrogen and surface is less than the interaction between the nitrogen with nitrogen molecule. Okay, so no adsorption can take place there. The reason why C negative is, let me go back, yeah, on this table. Let's say a particular sample where I have taken so many values from 0.05 to 0.3 for BT calculation, and I find that C is negative. That can happen if the sample happens to be a microporous sample. So what is the next step I should do is, what I should do is remove some of these higher pressure points, and if we have lower pressure points which we didn't take in the calculation, we should include some low pressure points here. So instead of 0.05, let me start at 0.001 and then do the calculations. When you do this, removing the high pressure point from the BET calculation, then you will realize that your C value tends to become positive. Now that means why it was negative, because you were using wrong range of pressure points for calculations. Okay, that is one of the reasons. So we will see these results later on when we are seeing some of the results, but that is one of the reasons. It's a wrong BET range. That is one reason. Another reason could be, as a matter of fact, the pores are so small and there is no open surface, which means it's only microporous surface. The pores are so small that there is absolutely no chance of any multi-layer adsorption. Okay, BET applies only with the multi-layer range, because when if you just a minute, let me go back. Okay, this is an isotherm. Your monolayer is complete somewhere here. Okay, from this to this particular range is multi-layer range. So BET equation is applied in a range which has just started, or with just before the monolayer is complete, and then into the multi-layer. That is the region which is BET region. Just before the monolayer is complete, and right up to the point where it has already formed few multi-layers. Okay. But in some cases, no matter what juggling you do with the points, whether shift those points into the calculation, take those points out of the calculation, no matter what you do, you will never get a negative C value. Okay. In such cases, you really can't calculate BET surface area using that data. Something else needs to be done, we'll talk about it. Negative y-axis, negative y-intercept, once again, not allowed. If negative y-intercept is taking place, once again, you can't, that means the data range is not correct, or the BET validity is not there. Then the BET validity to your data is not there. Okay. Okay. I'm not I'm not showing that set of 6 isotherms, according to IUPAC. You must remember the first one of which was a Langmuir isotherm, okay? Calling it a Langmuir isotherm, actually in physics option studies, the isotherm that you get for the micropolymer materials is like a pseudo Langmuir isotherm. It's not a perfect Langmuir isotherm. Perfect Langmuir isotherm you get only in chemical reactions, not in physical adsorption case. Because Langmuir thought there is only single layer formed and there is no possibility of any further adsorption. That is precisely what happens when there is a chemical reaction on the surface. And hence, for chemical chemisorption cases, chemical reactions, Langmuir models apply very nicely. When Langmuir was doing this physics experiments and gave his model, he was basically working on carbon materials, activated carbons. And activated carbons, his theories, this Langmuir model worked perfectly well. And because that was the only material he was studying, he thought he has come out with a very nice adsorption model. Obviously, when people started studying other materials, they didn't find any validity for Langmuir model, and hence somebody else had to come out with, not somebody else, but Brunner, Emmett, and Taylor had to come out with this combined theory of multi-layer adsorption. They extended the Langmuir theory, included possibility of the multi-layers, and then came out with that equation that I showed you. The beauty of this equation is that from an experiment or from the data which has multi-layer formations, they are giving you value of the monolayer capacity. And that is the beauty of that BET equation. From an experiment consisting of multi-layer adsorption, you are determining what the monolayer capacity is. And that's why I said that BET range should start just before the monolayer is complete. If you have started the BET range after the monolayer is completed, then it's not a good BET calculations. Let me give you an example here. This is a good example as to how BET should not be calculated. This is a value, BET surface area is 405. Okay, C value is negative, Y intercept is negative. The graph also shows this. Instead of cutting Y axis, it is cutting on the X axis. Now, if you see the points that have been taken are 0.06 up to 0.19. Obviously, a lot of points were changed from, higher points were removed and the lower points were only there. Even then, they couldn't make the C positive here in this case. What is the monolayer capacity that it is showing? It is showing a monolayer capacity of 93 cc. Okay. When you look at this table, the quantity adsorbed is the first quantity adsorbed is 114. And then it goes up to 120, which means it is trying, the equation, and that's a good example that you must appreciate. No matter what equation, what God-sent method you are using, but you are trying to calculate something in this range. From this range, you are trying to calculate something, the value for which is much, much lower than the first value. That means you are trying to, not extrapolate, but interpolate your results. And that's why that's not a very good method. From this curve, if I had got the value, monolayer capacity of between 114 and 120, it would have been a nice calculations. It would have been a nice application of this BT equation, because from so many points, I'm trying to find one particular point which is within the range that I've used. Here, you're trying to find a value which is outside the range that you are using. Okay? And that's why it is a very wrong way of calculations. Your monolayer capacity should be in between the values that you have used for calculations of BET. That is what I'm meaning to say. In such cases, once you have tried everything, still the C doesn't become positive, or y-axis doesn't become positive, the best way is to apply a Langmuir model. Okay? And Langmuir model will give you a surface area which it says 405 here is 502. A clear jump of about 20%, 25%. Okay? Another example, activated carbon, you will have negative C, negative Y, try to change the values. The C has become positive. The surface area value, which was earlier 1326, is now, after you remove the higher points, has become 550. Okay? And it's become 1450, and with the C value has become 550 positive. This is a good case to show, although y-intercept is positive, your C is positive. Look at the monolayer capacity, 335. And what is the quantity adsorbed here? Quantity adsorbed range, 338 to 389. Okay. This also is an indication that your calculations are not good enough. The validity, BET validity is not good. The QM value has to be in between this range. QM value or monolayer capacity value should be one of these values or between these values. Then only the calculations are, I would say, of some quality. When I apply Langmuir, actually the surface area is about 1736 from the original 1400. Again, a difference of about 30% here, 25% between BET and Langmuir. In fact, better. I know most of the students who get their samples analyzed outside, they just get a value of the BET surface area which they report or which they consider as good. When you get some analysis done by somebody else, if you are doing the analysis, you will see these things anyway. But if you are getting it done, look for something when you want to see how good the BET surface area calculations are. These values are, you must, if any of them is not there, then you start doubting the results. So, after the BET range is, discussions on BET range is complete, we will now move to the pore size distribution. Pore size distribution means IUPAC classification is a good class. It has changed now. This classification has now changed. As a matter of fact, micropores and mesopores both have been merged into one, and they have started calling them nanopores. Okay. We are more like classical people. We don't like this classification ourselves, but IUPAC is recognized by everybody. It's like a Supreme Court. We have to abide by it. Micropores and mesopores nowadays are known as nanopores and macropores. why I like this classification is that why I like this classification is because it tells you there is a basis on which it was done. There is a basis on which micropores were called any pores less than 20 angstroms or 2 nanometers. Mesopores were between 2 to 50 nanometers, and macropores were greater than 50 minutes. Let me tell you in brief what these things are. First two demarcations were made because when gases are going into micropores in a different mechanism, the gases going into mesopores have a different mechanism. It's a shift in mechanism which decides what should be the limit of the micropores or where should the mesopores limit start. The end of mesopores limit is due to another reason. They say 500, and I think we talked about it yesterday. At least I spoke about it for some time. At around 500 angstrom, at around 15 nanometers, as I said, it's a class. It was done in 1984, as I mentioned here. In 1984, they were not very good. I mean, instrumentation wise, comparing it with what is available today, we were slightly backward in instrumentation. It was measuring any pore larger than 50 nanometer would have meant that we will be measuring the data at very close to the saturation. If 760 is the saturation pressure, we will have to be measuring, if we want to calculate pore size as large as 500 angstrom or 50 nanometer, we will be measuring the data very close to 760, means 755 or 750. That was a little bit difficult in those days because the instrumentation was not so advanced. Nowadays it is. So you can change this 50 to about, let's say, 500. Macropore, that was the reason why the mesopore limit ended at around 500 nanometer around that time. 500 angstrom around the time when this IUPAC classification was done. Okay. Now, if your samples are micropores, you need slightly different hardware in your instruments, because, as I said, okay, let me go here. This is a microporous sample. Okay. When we have to measure microporous sample, that means that we have to measure this isotherm data, right from less than 10 raised to power minus 7 P by P0 relative pressure onwards. That is where we have to make the measurements. Okay. In order to make those measurements, your instrument requires slightly more stringent conditions. Your instrument has to withstand a very high level of vacuum. Means you have to provide for a very high level of vacuum pump, because you have to measure data at a very low pressures. Your pressure transducers also have to be of a lower range. The normal pressure transducer, which means 0 to about 1000 millimeter torque, which is used to measure the 1 to about 1 or 10 to 1000 millimeter pressure, absolute pressure, will not be able to measure these pressures. So you have to provide for extra transducers there. All these things done. So if you are measuring your micropore materials, you have to select a proper instrument to do that. By the way, I don't know, doctor, the one that is in NML is capable of doing it, so that is okay. In this picture, there. Yeah, I mean, I think I thought let me digress a bit and tell you where do these different pore sizes come about. It's a very interesting thing, and that if that is clear, then you will know many things will become clear. You know, when you are making those particles, okay, when you are making those particles, the particles come as non-porous materials. Let's say you are using a precipitation technique to make some material. The initial size of the precipitate is a non-porous. Okay, but those people who are interested in making nanomaterials or nanopowders or nanoparticles, they know those things. If you can arrest this process somewhere, you will make a particle of a very, very small size. The precipitation process, if you can arrest it, you'll make a very nice particle. That's why most of the nanomaterials are expected to be non-porous. Okay? But when these particles, while precipitating, are allowed to grow to a particular size, and then after that, these particles start agglomerating. So, first thing is, initially, all is non-porous. But when they start agglomerating, then you see porosity. That porosity is the mesoporosity that you are seeing here. Okay. So mesoporosity actually comes when you, unless you can create mesoporosity by other means also. But naturally, mesoporosity will come due to agglomeration of non-porous materials. Now is the question, where does the micropores come from? Micropores are the result of your lattice structure, the way your molecules combine together to form the lattice, to form the material. Okay. So while micropores exist in the lattice, it is the intrinsic crystals inside the crystals in the lattice, crystal lattice. Micropores arise from there. It's not possible to create microporosity. There are methods, of course, by steaming and other things, but otherwise, mechanically, you can't create microporosity just like that. Microporosity have to come from the structure of the material. Mesoporosity come from agglomeration of the non-porous particles. Okay, so this argument will be useful when I'm talking about something else after we see the results. Well, this is an old slide, and my request will be don't give too much too much importance to this. You will never see. It will be very difficult for you to correlate with the slits and all this. I mean, you may see some different type of hysteresis, and you will start correlating wrongly to the slits or cylindricals. Among all these things, the first one is what I would like you to consider, because most of your results are normalized to the cylindrical shapes. They actually are not. And another discussion that I want to do is about the bottleneck, as to why bottlenecks result into this sort of hysteresis. Let us consider adsorption and desorption from this shape of the pore. Okay. Fortunately, unfortunately, my timing between 3 to 4 always happens when the afternoon tea comes to my table. So you have to forgive me when I have to sip a cup from the cup of tea. In the gas adsorption, the smaller pores fill first. You know, when you start increasing pressure, at lower pressure, the smaller pores will fill. Okay. So when you are adsorbing at lower pressure, this pore has started filling because the neck is narrow. It has started filling at lower pressure here, this pressure. And since it has got a bigger volume inside to fill, lot of gas will keep on going there. After you have reached this point, that is saturation, now you started dissolving the gas. When it starts dissolving, remember the gas has to come from all of this through a narrow mouth, narrow neck. And narrow neck will empty only at this place, which means what will happen? This thing should have come here, cannot come because of the restriction here. So as soon as you reduce the pressure here, all of a sudden the entire gas blows out. And that is the reason why it almost falls vertically to the x-axis. Because through the neck, this empties much later, and when it starts emptying, the entire volume has to come out. And that's why this is almost a vertical fall to this y-axis. Well, Kelvin equation. Okay, I think I have missed on a particular slide just to show how the pore looks like and how it is filled. We have a cylindrical pore. When gas adsorption takes place, while the layers were forming, layers were also forming inside the pore on the sides. And after certain pressure is reached, then the core of that pore starts condensation, which is known as capillary condensation. Actually, the pore size is calculated by using Kelvin equation to find the width of the central core, which means the capillary condensed core. The total pore size is this central core plus the multi-layers that have been adsorbing on the walls. Pore radius, R is a radius, pore radius equals to the central core radius plus the thickness of the adsorbed layer. Okay? Kelvin equation is used to find RK. Thickness equation is also used to find the value of T. When you add them up, you get the value of the size of the pore. This is the pore size calculation there. Kelvin equation will give you it's a relationship between pressure and where is R? Here. Pressure and radius. This will give you the radius of the pore which is filling at P. Add to that the thickness of the adsorbed layer which was already there before the pore starts filling. The two combined together will give you the pore radius of pore diameter if you multiply it by 2. in all these discussions, we have not talked about thickness. I'll spend some time on this on it. Let me first take it further to where. Okay. I'm missing on one more slide, which I thought I have. I think I missed on that slide. Okay. Doesn't matter. Well, desorption branch will collapse to adsorption branch. It happens mostly due to the connectivity pores, means what you call interconnected pores. And one more reason can be because of the tensile strength effect, the effect that which will, because of the extra force that is seen by the liquid which comes out of the capillary. That is what is related to the tensile strength effect. All this happens. Tensile strength effect brings the desorption branch abruptly to the y-axis, to the adsorption branch. If you are using nitrogen gas, that happens around 0.4 P by P0. If you are using argon gas, that happens about 0.27. Okay, this is where it is happening here. This is a carbon sample, but it is, look at this desorption branch striking very steeply to the x-axis. This can be seen in some other case. It can be seen in this case, for example. The slide that I was looking for was to show that it is, generally speaking, it is very normal and it is desirable to use desorption branch for pore size calculations. Desorption branch originates from a lower energy state. Talking in another way, desorption branch comes from a more stable state or more equilibrated state, and that's why desorption branch should be preferable for calculating pore size distribution. But this doesn't come without a rider. As a matter of fact, with very big rider. If, let's say, this is your desorption branch, if you are calculating pore size distribution using this branch, then this is what you get. This is your pore size distribution. Okay. As I said, no matter which sample, no matter what you do, you will always get a pore at 40 angstrom. You will think that your sample has a pore of 40 angstrom size. Now, frankly speaking, there is no pore of 40 angstrom size in your sample, basically. Because if there was a pore of 40 angstrom, while adsorption branch was being measured, this activity should have been there, right at this place. Where this activity is shown on desorption branch, there should be an activity on the adsorption branch also. If the adsorption branch had started increasing like this at this point, I would say there is a pore of 40 angstroms in your sample. But if you look at the adsorption branch, the adsorption branch goes quite smoothly right up to this place, without showing any pore sizes being present at this point. So this pore size that you are seeing in your desorption calculation is because of this fall, this line that is coming down to meet the y-axis, coming down to meet the adsorption branch. It's because of this fall that you are seeing a nice, quite narrow peak of your pore size, showing pore size. It is not a true pore size. And that's why it's mentioned artifact. There is no pore of this size. It is being shown to you because you have chosen a wrong, you have chosen a desorption branch for measurement of pore size distribution. Please be careful. It looks very beautiful. I mean, if somebody tells you, my pore size is 40 and shows you this graph, it's a nice peak. You will say very, very, very good peak. It's a wrong peak, unfortunately. Another thing I wanted to mention was nanoparticle measurements. Many of you will be doing nanoparticle measurements. Doctor, do I have time? I'll take about
Yes,
10 minutes.
Yes, sir. Yes, sir. No problem. Please, sir.
Because this is a common problem. I'll tell you, a lot of people face it. A lot of researchers face it. A lot of other people also face it, let me say. This one is a nanoparticle, a silica nanoparticle. Okay. It's a nanoparticles available from the shelf. I think ICM silica nanoparticles. If you take isotherm, if you do gas adsorption isotherm, this is how it will look. And what does it show? It shows that it shows some hysteresis here, and you will think that this is due to the presence of mesoporosity, isn't it? Well, there's nothing wrong in that. Anybody should think that way. The problem is when these nanoparticles are put as a powder, okay? I earlier told you nanoparticles are expected to be non-porous. When these non-porous, very, very small particles are put in the form of a powder, they have a lot of void space. And normally, no matter what size, but whenever you put spheres together, they will always have a void space. Okay, the size of the void space, which is basically what these pores are. The size of the void space depends on the size of those spheres. When it's nanoparticle, the size is very, very small. Size is so small that the void volumes fall in the range of mesopores. Okay, and that's why it is a void space. It's a void volume which renders itself to be as good as a mesopore. How do we know that it's not a mesopore, it's only a void volume? One way of finding out is, it should come to you through experience or through prior knowledge of your particles being nanoparticles. But a confirmation can come from the fact that if this were a mesopore, with this were a particle porosity, its size is about, it's very close to about 500 angstrom or 1000 angstrom pore size. When you measure the particle size of your nanoparticle, it may be about 100 angstrom. So we are talking about a 500 angstrom pore in a 100 angstrom particle. which is not possible. So, which says which shows that this is not porous. This is not particle porosity. This is basically interparticle voids, which are which fall in the size range of mesoporosity, and that's why it shows up as mesoporosity in the isotherm. It is actually void. Be careful, because I'll tell you why I'm telling this is, otherwise you will almost always end up in a situation that my nanoparticles are 500 angstrom porous. That will be the result you will be presenting, and God forbid if in the same paper you also publish what the particle size is. If you say 100 angstrom or 10 nanometer particle and 50 nanometer pores, that raises a lot of questions. Okay, so be careful when to measure porosity and when to measure voids, especially when you are dealing with nanoparticles. Obviously, when you do BGH, it doesn't have. I mean, it's a very, very wide. Look at the y-axis is the pore volume. Look at the pore volumes. 0, 0, 1. Actually, there's no pores. There's no volume in the pores, basically. That is what it means. Well, this is how, if an unknown sample has to be measured, this is how you should try and find out how to degas, what degas temperature should be used. Basically by measuring multiple surface area multiple times by varying the degas conditions and seeing as to which conditions give you the maximum surface area, and that condition should be chosen as the condition for all future analysis. How important the preparation temperature is or preparation conditions are, somebody asked that question yesterday. This is one sample. This is an isotherm plot. Doesn't look like an isotherm, it's a wrong isotherm. Okay, this sample was prepared at 90 degrees. I'm sorry, 90 degrees for 2 hours. Okay, the value adsorbed were negative, all those things. When I prepared it at 100 degrees for 12 hours, now the isotherm looks like nice. Okay, it's a low adsorbing material, all right, but still material adsorbing, it has to be a positive adsorption. In earlier case, there was no positive adsorption, which means the preparation was not perfect. Okay, I will rush through this. I want to talk about 2 or 3 things which are very important. At least one of them is two of them are very important. Another gases that you use for adsorption, especially for microporous samples, is argon. And if you are studying carbon materials, activated carbons and things like that, then you can also use carbon dioxide. Okay. Carbon dioxide offers you many advantages. If the material, if you can use it, it offers many advantages. The whole experiment can be finished within about 2 to 3 hours or 4 hours maximum, while nitrogen or argon might take about 24 or 30 hours. Plus, it's a good measurement. Models are there for carbon dioxide adsorption on carbons, and hence you get a nice calculation of your pore sizes, micropore sizes. This is carbon analysis basically. Well, you will have this. You will have these slides for future reference. But IUPAC, which everybody wants to follow or do, everybody does follow. They also insist that while presenting your gas adsorption data, you must mention all these things. For surface area calculations, these things should be mentioned. Gas adsorption results. How do you make sure the gas adsorption results? First thing is, I was talking about, okay, that I'll be talking about in the next 1 minute or 2 minutes, all this thing. But these slides are there. Please go through them. These are the important things that you must appear in against all the adsorption